Good morning all. I've been doing some more playing around with this iSDT BG-8S it is. It's an 8-channel voltage monitor for lithium-ion batteries. Now this is a lithium-ion phosphate LiFe04 I think it is battery. 8 cells, so all 8 voltages will show up on this, but I just wanted to show what happens when it goes into kind of sleep mode. You get this, what they call the breathe LED. Now that sort of nondescript color is actually the red, the green and the blue little segments of the LED, which are fading in and out, which is I think why they call it breathe. And that means that this unit's gone to sleep. And it does seem that it uses very little power when it's asleep, just driving that LED on and off. Because if I switch it back on, this has been connected all night, and the voltage hasn't really dipped at all. It was 26.28 last night, so this has probably been sat there for 12 hours doing that. You can see the 8 voltages there, and you can see the 6 millivolts difference between the cell voltages. That breathe LED, which was all 3 colors, is meant to represent sort of white or gray, and this is the gray screen. This is simply the cell voltage monitoring screen. You can go into the menu and start a cell balance, and then it goes into the green screen, and here you can see that it's actually discharging cells 2 to 8 in order to bring their voltage down to match cell 1, which it's determined is the lowest voltage cell. So currently we've got 7 millivolts of difference. That's gone into dim screen mode. It seems that in the green mode, it goes into dim screen really very quickly, and I'm not quite sure why. The green mode will turn into a blue mode when the balancing is all done. If I go into the menu again and stop the cell balance, of course it goes back to the grey mode, which is just cell voltage monitoring. So I'm going to do a balance. So I just go in, start the cell balance. That goes into the green mode. The little terracotta coloured symbols light up to show which cells are being balanced or brought down in voltage. That will go into its low brightness screen very quickly. I don't know why they've decided that in this green mode it should turn the unit off so quickly, but they have. In the grey mode it seems to sit there for quite a while, but that's gone completely off. Now we've got the breathe light showing green, but for some odd reason the software writers decided that in the green mode it wouldn't breathe, it would just simply flash on and off, which is slightly odd, but there it is. So I'll just leave it like that for a moment while I rig up something to connect to this main power connector. Let me just move the camera slightly so you can see the main power connector, which is there, because I want to try charging this pack while monitoring on here, or even discharging on here, balancing on here, at the same time as I'm charging using a constant current source on the main connector. So I need to rig up some power supply in order to charge this battery pack. So I'm going to use this. It's a Minghe power supply. It's the Minghe D3806, so 38 volts, 6 amps on the output. Now the interesting thing about this is it's buck boost, so I can put my 12 volts solar in there. In fact, why don't I do that right now? Here's the connector. Let's plug that in. So I've currently set that for, oh, that's gone all smudgy, but I think that's 12 volts and 1 amp. Yeah, that's right. So that'd be 12 volts on the output. Now I need a lot more than that to charge this pack, because as we saw, and probably as we can still see, the pack voltage is 26.26 volts. So this will need to be up to at least that. And I'm probably going to put a diode in the output of this when I charge this pack, so that the pack's 26 volts can't backfeed into this unit. I don't know whether that would cause a problem, but it might. So this is the cable that I'm using to charge the battery pack. There's this rather strange IEC plug with the earth going not the normal way. This ends in 2 banana plugs. Now if I plug that in there, and touch these together, there'll be an almighty bang. So, oh, that thing's finished doing the balancing now, and it's gone to the blue screen. So you can see that there's just 2 or even 1 millivolt of difference between the cells now. So this thing will have to be plugged into a couple of these terminal posts before that's gone off also very quickly. Actually, that's gone to its half brightness mode, and then it goes off, and now we get the blue breathe light, which means that you're in the balancing mode, but balancing is finished. Again, it's not breathing, it's just flashing on and off. Yeah, so these need to be connected here. I wanted to put a diode between these terminal post sockets and the output of the power supply. What I might do actually is put a diode on each one, one going one way and one coming back the other way. I don't know why, really just, I suppose, a mechanical thing to have something to connect into those screw terminals. So I'm going to solder these diodes onto here. Then I can use this to start charging the main battery pack. We can monitor the voltage on here in its monitoring mode. In fact, let's do that now. Let's go back to that screen, stop the cell balance. That goes back to the grey screen, which curiously seems to stay on a lot longer. This stays on for several minutes. The difference between the cell voltages has crept back up to 4 millivolts now, as they all sort of settle after having the discharge resistors placed across, I think, 7 of the 8 cells. So let's make this up and start charging this pack. Right, here it is. I've got output, positive output through that diode, out on the positive terminal, through the battery, back on the negative terminal, and back through the diode pointing the other way, and into the negative of the output of this unit. So that should do it. Let's plug in the cable and then plug that into my battery. Right, here it is. Power supply is up here on top of the battery, positive and negative terminals, bit of blue tack there to stop the whole thing sliding around. Let's plug in the 12 volt input. So that's saying 12, so that's going to need to be, well, at least 30 volts, I think, to charge this battery. And I think what I'll do is I'll set the current to about 1 amp. It's quite a big battery. 27, 28, 29, 30. Let's just make that nice and neatly 30. Okay, so current, yeah, that's set to 1 amp. So 30 volts, 1 amp should be fine. Right, let's plug this into the battery pack connector. Okay, that's plugged in there. And now I can switch the power supply on and then go back to monitoring this little monitor. So let's bring the camera back down here. We'll monitor on here the cell voltages. So it's currently 26.27. Let's switch this unit on and monitor current. So that's drawing 1 amp. And you can see that the pack voltage is climbing quite swiftly, or moderately, and we're seeing the cell voltage difference changing a little bit, rising perhaps a little bit. So we've got 26.5 volts with 1 amp going into this pack. If I move this over a bit, you can see the connector there and the connectors here going into the pack. So we're monitoring the pack voltage completely independently of the charging, and I can switch on the balancing. Now, of course, with 1 amp flowing through each of these cells, I think it's unlikely that this balance unit, this BG-8S, is going to be discharging the cells at 1 amp. So it's unlikely. It should be able to match them because it will still offset a bit of the current in these 7 cells. Is it 7? Oh, that goes off very quickly, doesn't it? Yeah, it's got resistors across 7 of the cells and not across the other one. So is it going to be able to match them by offsetting the current? Yeah, I suppose it should do. So I should be able to charge this and balance it at the same time. Now, of course, I'm balancing it at this voltage, 26.65. I can't remember what the maximum voltage of 8 lithium iron phosphate cells is, I can look that up. And in fact, what I could do is set a maximum voltage on here that would prevent this pack going over that maximum voltage. That's something I could do. So here we are, the Wikipedia article on the lithium iron phosphate battery. Let's go down to the specs. Here they are. So I think nominal voltage is 3.2. Working voltage, it says here, is 3.0 to 3.3. Minimum discharge voltage 2.5. So 2.5 times 8 is 20 volts, isn't it? So I can't take this pack below 20 volts. 3.65 times 8 is, I don't know. Let's work it out. Right, so 3.65, which is the maximum cell voltage, times 8 is, okay, 29.2 is the maximum pack voltage I can take this to. It's currently 26.74. So what could I set this to in terms of voltage? If I stop it, I can actually set the voltage to prevent the pack going over 29.2. I've got a couple of Schottky diodes here. Let's quickly look up Schottky diodes and see what their voltage drop is likely to be. I know it depends on current and temperature and all that sort of thing. I think it's about 0.3 if I remember rightly. Okay, so Schottky diode here on Wikipedia. Let's look at the, well, it says here, while standard silicon diodes have a forward voltage drop of about 0.6 and germanium 0.2, Schottky at 1 milliamp is 0.15 to 0.46. Okay, quite a wide range. Well, I'm driving this at 1 amp. So yeah, I suppose 0.3 would be about what we'd expect. I could measure it, I suppose. Yeah, so one of them is 322 millivolts, and the other one, if I can get that on there. Okay, 321 millivolts, so about 320 millivolts per diode. So if I turn this off and set it to about 29.6, I want to not go up to 29.2, I'll go up to 29 just in case there's some difference in the cell voltages. It seems to be, oh, that's up to 18 millivolts of cell difference now. But let's go up to 29 for the battery plus 0.6. So I'll go up to 29.6. Let's bring that down to that. 29.6. So let's store that at 1 amp. Switch that back on, and that's showing 27 there. So the battery should be about 0.6 more than that. No, 0.6 less than that. Yeah, about 26.8, 27.46. Oh, well, you know what I mean. Yeah, there's about 600 millivolts difference. Okay, let's leave that going for a while. Now, the question is, as these cells approach their maximum voltage, are we going to see a wildly increasing difference between cell voltages? And is this thing, because I doubt this is discharging at 1 amp, it's almost certainly going to be less than that. Is this thing going to have a problem maintaining balance while that happens? Let's have a think about that. So I've drawn a sort of discharge curve. Now I've done this for a LiPo. 4.2 is the maximum voltage. It will drop away from that fairly quickly, settle down. I've probably put a bit too much slope on that, but settle down at sort of the nominal LiPo voltage, which is 3.7. And then when it gets to 3 volts, it will drop off fairly quickly. I'm not sure whether that 3 volts should be a bit lower positioned, but that's essentially it. Now what I wanted to do was put another one of these in front of it and hope I can get enough light behind there and draw another curve. It's going to be similar, but what I want to do is start a little bit to the left, come across here, and then end a bit to the right. So there's our 4.2, there's our 3.0. And what I'm trying to represent here is two cells which are similar, but they have actually different capacities. So if you start them discharging at the same time, one cell will actually outlive the other because it has a slightly larger capacity. So I wanted to see what exactly is balancing. Well, top balancing is where you get the starting point for the cells both at 4.2 volts. And then as the voltage decays away, they stay very similar for a while, but of course the cell that has the larger capacity will last longer, and therefore it will drop down to 3 volts later. This is time, of course, running across here, later than the cell with the smaller capacity. Bottom balancing is where you get the two to coincide, reaching their minimum voltage of 3 volts at the same time. Well, of course, that's only going to work if you start discharging them from 4.2 at different times, or you discharge one of them to 4.2 and the other one at that same time, which is going to be this time period here, will start at a different voltage. And that's quite hard to achieve. You can bottom balance cells by simply making their voltages the same when they're at their minimum voltage, 3 volts for a LiPo. But typically when you charge cells, the charger is going to take them all the way up to 4.2. So charging cells is automatically going to top balance them like that. Now, this little unit here is balancing at a sort of middle voltage. So it's balancing somewhere in this middle section here. Now, that's much easier to achieve because the slope is so much flatter there. It's much steeper at the top end of the cell and at the bottom end of the cell's voltage range. So this unit is mid-balancing. It's balancing the cells at this midpoint, so they coincide at some time, like this time here. Well, of course, then their high voltage points won't coincide and their low voltage points won't coincide. So you can't top balance, bottom balance, and mid balance all at the same time. Now, these are discharge curves, of course, because as time travels from left to right, the voltage on the cell falls, holds in the sort of midsection, and then falls again at the end. Now, of course, I'm charging this pack. Let's have a look at the pack voltage. It's 26.83 as measured by this unit. Incidentally, this unit, if you didn't see my first look at the BG-8S, this was supplied by Banggood, very kindly supplied by Banggood. And in the description below this video, I will put a link to this device on Banggood's website. It is a sales tracking link, so they will be able to see how many people go through to their website as a result of this video. But going back to this, we're charging these cells, so we're starting sort of at this point and we're running up. Now we have very good balance between the cells of 6 millivolts, so they're very closely spaced. So say we're here in time, I have to slide these until these two lines coincide, but it doesn't mean that when we start to shoot up, now the maximum voltage on lithium iron phosphate, this thing keeps switching itself off, is 3.65 volts. So it's not 4.2, but the cells will start to shoot up one at a time. And so as we approach the 29.2 volts for the pack, I would expect to see this difference voltage, the maximum cell, this is for the maximum voltage cell between that and the minimum voltage cell. I would expect to see that start to really widen out as we get this sort of thing where one shoots up and then another one, because we're at this time point, isn't ready to shoot up. So that's what I'm expecting. So although I can charge the pack using just a constant current power supply, I do have to keep a very close eye on these difference voltages, because when that starts to shoot up, I know that one of the cells is going to be getting very close to its maximum 3.65. What are these on now? 3.35. So there's some way off that. But when that happens, I'll either need to turn the power supply off and do some more balancing, or certainly wind down the current on the power supply. So while this is charging, I just want to show you that this is not actually connected to the main power part of the battery. I've only got this connected to the 9-pin balance port, so it's powering itself from the balance port. It's measuring the total pack voltage on the balance port between the grey wire there at one end and the black wire at the other. I think the black wire is actually positive on this. It's giving me, well, it's measuring all the cell voltages, of course, the voltage between each of these 9 wires, and it's telling me the maximum difference between the lowest and the highest cells, which is now currently 8 or 9 millivolts, 26.85 on the pack. Right, now it's not very sunny today, so my input voltage here is down to 12.2. This is putting an amp out. You can see that 1.001 amps are flowing on the output side of the circuit, but that is at 27 volts. My input is only 12 volts, so there's 2 or more amps, and with inefficiencies in the circuit, there's probably 2.2 or something amps flowing on the input side of this. So I was just wondering if anything's getting hot, so I'm just going to feel these diodes. Well, they're just warm. They're not particularly hot. Interestingly, these heat sinks on the power supply itself are pretty warm. That one's very warm. Don't think I can leave my thumb on there for very long. That's quite warm. This one's not so bad. One of them I think is the MOSFET and one is the diode. Or does this unit have, I can't remember now, does this unit have one of those 5-pin integrated circuit switch mode regulators? I can't remember. Well, from the underside of the board I can see that, if I can get the light level right, that is a 5-pin device and that is a 3-pin device. So yes, I think in the buck section it's using one of these 5-pin switch mode regulators. In the boost section I think it's just using a MOSFET and a diode. Well, we've still got a very modest 5 millivolts, 6 millivolts of difference between the cells, so I probably don't need to be in the balance mode just yet at 26.8 volts. So let's stop the balancing and go back to the standard just cell monitoring mode, because it does seem to keep the display on longer in this mode. You can see now that the difference between the cells has drifted up a little bit because the balancing resistors are no longer being placed across these wires. So yes, I'm just interested in how far that drifts up as I approach the maximum voltage 29.2. Yeah, it's just of course occurred to me that the cells inside this bike battery are 10 amp hour and I'm charging at 1 amp, so it's going to take 10 hours to charge this pack. Now of course it's partly charged already, but this could take a while. I might have to come back a bit later. So I've increased the charge current to 1.4 amps. I did go up to 1.5, but it started squealing quite a lot. At 1.4 amps on the output, we're probably drawing, well, probably getting on for 4 amps on the input, and that is having an impact on my battery voltage. It's dropping quite low, actually. You can just make out there on my little voltage monitor that the batteries outside are down to 11.7, 11.6, so it is struggling a bit. Now, I mean, that's probably more to do with voltage drop in the various wires and cables than actually genuinely 11.7 on the terminals of the batteries outside, but when it drops that low it does start to get a bit alarming. Right, I've dropped the current to 1.2 amps because the batteries outside were suffering a little bit, down to 11.6 at the moment. The pack voltage is up to 27 volts, but we are now starting to see one of the cells surging ahead a bit. It seems to be cell 7, 3.382, and the lowest one is 3.362. So there's 20 millivolts of difference between the lowest cell, cell 3, and the highest cell, cell 7. So I'm expecting that what's happening is cell 7 and cell 3 are like this, and cell 7 is now starting to increase its slope as it pushes up towards its maximum voltage. Cell 3 is going to be much later. Of course, time is running this way to the left, and if I rebalance them, what I'm effectively doing is sliding the two graphs one on top of the other, and I can get them more closely balanced so that when we hit the maximum voltage it'll happen at a much more coordinated time. So 22 millivolts now between the lowest and the highest, and I expect that to start accelerating up, that difference between the lowest and the highest voltages. So let's start a balance running and see how that difference between the lowest and the highest cells come down. The lowest cell it has identified as cell 3, which is what I said. It's actually bringing all the other cells down because they're all higher than the lowest one, of course. I doubt it'll have much impact at 1.2 amps flowing through this main connector here. Of course, this thing goes off very quickly. But I may be able to hold that voltage differential there and stop it really climbing away. Of course, I may not, so I'll just sit here and watch it. Right, I've stopped balancing now and allowed the cells just to be monitored by this monitor. I have to say that for someone who quite enjoys watching paint dry or watching grass grow, this is great fun. I haven't had this much fun in ages, just pumping 1.2 amps into this battery pack and just monitoring these cell voltages. Oh, that's gone off. This is wicked. So up to 34 millivolts of misalignment. Actually, the highest cell now appears to be cell 6, 3.397. So just going back to this diagram again, just to sort of try and drum this in, what's happening here is we've got misaligned cells. We've got cells whose top points are not in the same time position. And by forcing a current into this pack, we're effectively moving our time marker along. And as we move it along, you can see that the difference between the highest voltage cell and the lowest voltage cell start to diverge as we move nearer and nearer to the maximum. Time is running right to left in this case, to the maximum voltage for each of these cells. Okay, so that's sort of crept up now to 35 millivolts. So yes, it's this divergence. Now if I turn this current off and balance these cells, what I'm effectively doing is sliding these two graphs to realign this top voltage point. I'm showing this as a LiPo 4.2, and then I'd find that having balanced them, if I carried on charging, this discrepancy between the minimum and maximum voltages would be less dramatic because the cells have been rebalanced to have top voltage alignment. And as I said earlier, if you wanted to bottom balance cells, you'd simply balance them at a lower voltage so they have bottom voltage alignment. Right, it seems that actually cell 4 has taken the lead now, because that's bobbing around at 3.399. Oh, why's that gone off? Because I've been sat watching it. 3.399, and it's just nudging up to 3.4 volts. There's 34 millivolts of difference between the highest and lowest. And in fact, these bar graphs are also quite handy. You can see that the lowest by some distance, I can't see this on the screen of my camera because the timer clock is right on top of it. So looking at it directly, 3.365, and this one is 3.399 or 3.4 occasionally. So from the bar graphs, you can quite clearly identify the cell with the lowest voltage. I'm not quite sure how the unit rescales these bars for the overall voltage. I'm not sure how that works. I haven't been watching it long enough. But yeah, 3.4 volts just appearing there occasionally on cell 4. Cell 4's in the lead. It's like watching a horse race, isn't it? My God, I'm such a nerd, aren't I? Right, it's sometime later and I'm still charging at 1 amp. It's evening time and the lighting's a bit strange. Oh, that's just dropped to its dim mode. Let me put that back to bright, but probably can't see it, so I'll just see if I can redo the lighting. So this is now crept up to 70 millivolts of difference between the highest cell and the lowest cell. It's moving quite rapidly now, so you can visibly see it moving. The highest cell is this one, I think, 3.47. The lowest cell, in fact, you can see it from these bar graphs a bit more clearly now. 3.41, I think, is the lowest cell. 3.472 is the highest. Yeah, this is climbing up quite quickly now. So I'm guessing that one of these cells, which is presumably this one, cell 6, is now starting to make its final approach to the maximum voltage, which is, well, Wikipedia said it was 3.65 volts. And a few moments later, and we're now up to 100 millivolts, that's 0.1 of a volt difference between the lowest and the highest cells. And now it appears to be cell 8 that's accelerating away, 514. The lowest cell is 3.41. So there's your 100 millivolts difference, your tenth of a volt, 3.41 and 3.51. And that's moving quickly enough now that we can see it. This will be hitting 3.52 really any second now. And at this point I thought I'd better just check these headway LiFePO4 cells. It's this cell, the 10 amp hour. It says charging voltage is 3.65 plus or minus 0.05 volts. Nominal voltage is 3.2, capacity is 10,000 milliamp hours, that's 10 amp hours. So this is the point at which I have to start watching this 8th cell here, number 8. We've got 200 millivolts now of difference between, oh, that's the unit changing its lighting level. So that's 3.62, that mustn't go over 3.65. So it really is starting to race ahead now. So at this point, I'm going to have to stop this charge or on the power supply, or at least bring the current down very significantly. So I think I'll just stop that. These will all fall away now, and you'll probably find they all start to equalize. The difference between different cell voltages is starting to equalize, and now really the only thing I can do is start a cell balance and just leave it for a while and see if it can bring these cells into balance, and then I'll start doing another pumping of 1 amp of current into this battery until I've got all the cells up to the maximum voltage of 3.65, and that of course would mean they're all top balanced. So yeah, that's been good fun. I've enjoyed that. Let me just check where the balancing is now. It's down to 49 millivolts, probably mostly due to the cells just realigning themselves with each other. But that balance will eventually bring that down to 0. But yeah, enjoyed that. Cheerio.